Okay, I've been asked to provide some explanation and discussion of one of our homework items, and that was what I call a diving board. We've got a beam that is supported here over 30 foot from A to B, and then it has this overhang from B to C of 10 foot. That's the cantilever portion, and it's supporting a relatively light load tributary to the beam of 120 pounds per foot. The beam itself is a steel beam. It's a W10 by 22 with a second moment of area of 118 inches to the fourth, and of course the elastic modulus of steel is 29,000 KSI. We've been asked in essence to find the maximum displacement and the displacement out at the tip of the overhang. So presumably, because we have this 30-foot span in here, we might end up with a maximum located between those two supports, or it could be out here on the edge. What we're going to do is break this example up into a whole series of different parts. This first part will be all about the beam statics. Right, so of course we're going to go find the reactions in the way that you learned how to do in your statics class, and this reaction at B will be the larger one at 3.2 kips, and the left one is at 1.6, from which we are then going to create the shear diagram. Note that the slope of the shear diagram is going to be given to us by the load intensity, and so these two slopes are going to be the same, and we've got, because of the uniformly distributed load, then the shear diagram goes and integrates that load, a constant, into a linear function. That's what we've got, two linear functions, same slope. And we have the 1.6 at the left. We drop off then 120 pounds for every foot. That's 30 feet, so we end up dropping off to a net of a -2 over here at the right, spike up by the 3.2 kips, and then we're going to fall off then from there down to 0 on the shear diagram. Those distances that we've got here, of course, is 10 foot out here at the outer edge. And then, though, we're going to want eventually, for all kinds of reasons, to know where the moment is maximum, and that's where the shear is 0. So we find out by just similar triangles here that that's going to happen at the 13.33 feet distance. And then because I'm looking ahead and how I'm going to draw the moment diagram, I know that if we drop down at 120 pounds per foot from 1600 to get to 0 shear, then that same distance over here is going to put us ultimately at a -1.6, the same distance away from that 0 shear location. Right? And the leftover distance then is the 3.33, add all that up, and that's 30 feet. And so then you come down to the moment diagram. Of course, the change in the moment is given by the area under the shear diagram, so we start at 0 at that simple support, and then we'll increase by the area of this triangle. That gets us up to 10.67 kip foot. It's a second order variation because, of course, we're integrating a linear function and it becomes second order. And then that same function then drops down and will take us all the way down to -6, which does match the cantilever portion, right? We'll have W times this L prime, or 10 feet. That will be the total load out here, located at the midpoint of that 10 foot. So WL prime squared over 2 would be our -6, which is what we're going to have out here at the far right. It too is a second order function, and a couple of things that we need to take note of here is that regardless of how we pulled out the French curve to draw our little second order curve, note we're going to have 0 slope at the right because the shear is 0 right there, and then we'll have a big positive slope here at the support, or just to the right of the support. That's important to note that that's going to be a second order parabola. That's redundant, right? It's a parabola with a vertex over here at the far right. This other part is also a parabola. Its vertex is right here at the 13.33 feet location, and that's going to be important for us later on as well. We're going to want to know where that moment is equal to 0. That's an inflection point for the deflected shape. And since we're going to calculate displacements, let's go get that qualitative deflected shape, and we'll just get out our French curve again and match what we've got here. Positive moment means smiley face in that region, and then on all these negative moment areas, or hogging curvature, that's concave down or frowny face. We got here a couple of real important points to note. Again, the moment equal to 0 is where the inflection point is, the change from concave up to concave down. But it does not mean the displacement is equal to 0 there. It's not. Instead, that happens right at the support itself. Right, so we've got a reasonable qualitative deflected shape. I'd like that to be a little smoother right there in that transition, but sometimes when that inflection point gets real close to the support, it's difficult to get that in there in a nice way. What you're going to see later on in other parts is that we'll draw a nicer version of this as we get ready for the calculations. Right? Note some other things that I did too. I don't know what happens out here at this tip. I don't know if it rides up, meaning the middle span effects overwhelm the curvatures that are happening out in the cantilever portion, or if that tip at the end actually comes down a little bit. I don't know. And actually it doesn't matter. All we want to make sure of is that we've got the boundary conditions met, we've got concavity that makes sense, and that we've allowed things to displace where they can possibly displace. In other words, don't show them as 0 if they're not really going to be 0. Right, so that gives us a good starting point from which we'll be able in the succeeding parts to go calculate our delta max and our delta C.